Thank you. It's a great pleasure to be here. Thank you to the organizers. Thank you to Tiago especially, and to Dima and Edson for gathering us all together. I have some good news and some bad news. The good news is that my talk will be about billiards, or more generally about twist maps. And the bad news is that almost the entire talk has been prepared during the last couple of weeks. I actually tried to translate some of the ideas for 2.5 degrees of freedom back into the twist map setting. I'm pretty sure the things work, but I haven't had time to write it carefully down and check everything. So we are where we are. Actually, the last section is absolutely correct because it's written down and posted and submitted, and the first 5 sections are interpretation of this, but I think it will be interesting. I'm not claiming I have some very new results in twist maps and billiards, but it's a little bit of a different point of view, which I think it's useful, and maybe some tools. I'll be very happy if any of you have ideas how to use some of the tools I will present today. So what it is about, I'm trying to understand this. Since I was doing my PhD, this is this famous conjecture of positive metric entropy of standard map, and everything related to that, how actually this region of instability in a billiard, when we have mixed behavior, how does it look? So this is the context of my talk. I will start with just reminding you of 2 measures of transport and chaos. The first one, Raphael made a great introduction in a way in the talk, because the first one is the flux through a gap in a Cantori. This is exactly the quantity that, Raphael, you were calculating, estimating, a really nice talk for actually rational numbers convergent to 0. This can be defined for an arbitrary real number. And the second quantity is just the angle of splitting of stable and unstable manifold. I will remind you of some great results, in particular what Vasily, together with a group of people, has done. And so the main idea is actually that I will propose a third alternative measure of transport, which I'll call delta 1. And I'll explain why I call this delta 1. And the first 2 I call delta 0 and delta 2. And this delta 1 is actually going to be related to both delta 0 and delta 2. And it's going to be greater than 0 if there is no KM circle. So whenever there is no topological obstruction of diffusion, this delta 1 will be greater than 0, otherwise it's 0. And it's related to topological entropy and speed of drift close to an Aubry-Mother set with this rotation number. I will define this delta 1 and show why I think this is an interesting quantity. Then, the main topic of the talk, the idea is I'm trying to find ways to actually construct, embed invariant measures with positive metric entropy. So embedding, if you wish, chaos in a standard map or in an area-preserving map. And I will present some abstract tools that actually work for twist maps, but also work for Tonelli-Lagrangians in high degrees of freedom. So then I'll come back to twist maps, show how one can construct, using these tools in a relatively straightforward way, lots of positive metric entropy measures, and actually estimate their metric entropy, and also by variational principle topological entropy. And the goal is to try to at least partially describe really statistically what happens in the region of instability. It's like really a goal. We are still far from that, but this is the goal. And finally, this is what I know I can do. So these are really precise results for generalized Arnold's example in 2.5 degrees of freedom, where the same techniques work, so I believe these techniques work also in higher degrees of freedom. But I will focus today, I will actually present all the ideas in the case of area-preserving twist maps. I've given the first time this talk actually in London, when it was basically just some early ideas and qualitative results. Today I'm going to present a little bit of quantitative results. Okay, so just a reminder, this is the setting, area-preserving twist map. Here the assumptions are if it's defined on the entire annulus, but it works if it's just defined on a strip, like if you have just a billiard, everything works fine. I will assume that the generating function h, I will continue using this letter h, it's just C3. But it's not a necessary restriction, so, well, it needs to be C3, but if it's, say, analytic, then one can say a little bit more. But C3 is enough, probably even less, but I haven't checked. Okay. Now, 2 measures of transport. This is the first one. So this is closely related to Raphael's talk. So this is the famous paper now more than 30 years ago, if I calculate well, by McKay, Mice and Percival in Physica D, when they introduced this notion of flux through Cantori and actually explained of flux through turnstiles, and then they explained and developed really a very nice model how this transport could work in area-representing twist map. So what this picture is showing, it's actually showing, this is just a copy from the paper using computer graphics as of 30 years ago, but it's still, I don't think one needs to try to do better. It's a beautiful picture. So there are two counter sets which are marked. They're very irrational, so very small letters here. They're related to golden mean, so they're really very irrational in terms of their fractional expansion. And you can see, so what they've done, they started with 4 orbits starting here in this box, and then they stopped once these orbits reached this box. And you can see how this density actually, how really this Cantori form a barrier. Now, they calculated by a very simple method. So there are different ways to define this. I call it delta zero. It depends on the ratio, on the rotation number. So in this case, if rho is irrational, then this delta zero is the difference of actions of so-called minimax homoclinic and any minimizing orbit. So basically they take this y to be a gap of a Cantori and x to be a homoclinic orbit sitting somewhere in the middle. And it's a very, very simple evaluation. So this is delta zero. This is difference of actions. In this irrational case, you need to sum really over the entire z. Raphael, you have shown an alternative definition for a rational number where you really look at difference of actions between minimal and minimax periodic orbit. They're actually different definitions. And by the way, I haven't really seen, and Raphael, maybe you can help me, I haven't seen any precise evaluation why this delta zero is really related to something like topological entropy. So the arguments are clear. There is an explicit calculation that actually through a gap and Cantori, this is exactly the quantity of flux that goes on one hand side in this direction, on the other in the other direction. But this argument doesn't prove a priori that what happens to my kid, my small kid, when he goes into supermarket, you know, he goes into turnstile and keeps walking around. So it's no chaos, it's just a periodic orbit. So this argument doesn't exclude this possibility that you actually have a full measure of orbits just going around and no chaos and so on. So one of the results today is I will reduce this to a very plausible conjecture why this delta zero really measures topological entropy near this Cantori or near periodic orbit. So I'll come back to that. So my delta 1 will be closely related, I believe, to delta 0. The second measure of transport is the angle of splitting of stable and unstable manifold, and I'll show beautiful work, Vasily, where this is your result, but I'm sure you will say lots of people before you provided some ideas, but your paper in 99 is really nice. That's Lazutkin's formula, but your proof. You were the last, you were the final one who put this all together and resolved all the numerous technicalities. Yeah, so I just copied it from your translation of his paper, so I haven't checked. Anyway, it's exponentially small in epsilon, so this is just a standard map. So what is this? This is, I put this notation, I'm using the notation delta 2, and this is the rotation number. In this case, this is 0. This corresponds to a hyperbolic fixed point. So this is 0. This is a copy of it. And then there is, this is this angle alpha, which is really exponentially small for epsilon small. Now, why is this related to the topological entropy? Because now you have a uniformly hyperbolic set, which consists of this point and a homoclinic orbit, and you can, by a shadowing argument, you can embed a Bernoulli shift, and you can even estimate topological entropy. Okay. Now, I'm going in a couple of steps to define what I call delta 1. And then I'm going to show how this delta 1 is related to delta 0 and delta 2. So again, the first step is to define relative action. The ideas come from PDEs and from the methods, energy methods in PDEs. So I'm going to use letters that I'm used to use when I play with dissipative PDEs. Then this is really the energy. In this case, this is the action. So I'll do it just for an irrational row. It works also for rational row, but I'll do it for the irrational one because I believe it's a little bit simpler. One takes one reference minimizing orbit, so one orbit in a Aubrey-Mather set, and then y is just a perturbation, and one measures difference in the action between x plus y minus x. It suffices that if this y is in this space, and then this is convergent, so this is really well defined action. So basically I perturb the minimizing orbit, and all the interesting orbits that I care about, including homoclinics, are of this type x plus y. Then the second step is also very standard, is to define a Peirce barrier, which is actually, I look at the value of this action minimal if I fix position of, say, 0 coordinate. So just to step back, I will always be working in a variational space, so I will always be looking at xk sequences. X is equal to rz. So x is equal to xk, k equal to z. And then if this sequence satisfies this relation, then I know that this is a real orbit of the standard map. And for billiards, this age is just, as Raphael Jucha mentioned, and a few other people, this is just the Euclidean distance of, and x is a parameterized, say, convex, smooth circle, a boundary of a billiard. So this is the setting, and this is just the Peirce barrier. This is from Aubrey-Mather theory introduced by both Aubry and Mather. This actually measures what is the minimal action in this space if I fix position of y. So this basically means what is the smallest action of, if this is, I think we call it z. One wants to find some sort of quasi-orbit which has the minimal, in this case with rotation number with the minimal action. So if one fixes the coordinate 0. And then this Peirce barrier is equal to 0 if and only if there is no KM circle with this rotation number. And this delta 0, so this is the first quantity flux through Cantori, is really the maximal value of this Peirce barrier. This is just an alternative definition. Yes? Yes. Yes, I'm cheating a lot, but then it's by definition 0. Okay. So it's missing, okay? And all, so this is 0 if z is not in a gap, and if it's in a gap, then you just do this. So this line is missing. So if z, if you project the Aubrey-Mather set to a circle, if it's within the projection, then by definition Peirce barrier is 0. No, not homotopically trivial, so it needs to go around. Yes. Actually, I want the minimizing one. I really care only about, at this stage, I only care about Aubrey-Mather set. So this is just for fixed rotation number, it can be a circle, or if it's really rational, this is a Cantor set. Yeah. Yeah. Fair enough. Yeah. I don't care about elliptic islands here in this. So. Yeah. Yes, that's correct. okay, so I'll stand corrected. These are O'Brien matter sets which project onto to the entire torus. So this is what I mean when I say Km circle. It's a little bit okay. Stand corrected. Okay. Now definition of delta 1. The second step is again using the terminology from PDEs, the action dissipation, which basically is just summing square of this value. So if we have a real orbit, then this is equal to 0. And if it's not a real orbit, then it will be something strictly positive. And again, in this space, this will be convergent. If x is real orbit, so this can be easily by mean value theorem shown that this is convergent if we take this in this space. So in a way, this number d is equal to 0 if and only if x plus y is an orbit. X was by assumption an orbit. And this dissipation measures how far is x plus y from an orbit. So in a way, we look for, if we want to construct real orbits of our twist map of a billiard, we look for y's such that this quantity is equal to 0. These are real orbits. And now, what is the definition of delta 1? Associated to one gap in a contour. Again, if we have I'll still call it Km circle because I'm lazy. Then this delta 1 is equal to 0. So what is this delta 1? Delta 1 is, we fix one, so I will say energy level, so the action level. We look at orbits which lie entirely, quasi-orbits or potential orbits which lie entirely. This is a partial order on the set of all sequences which lie entirely in the contour. Actually, here should be smaller or equal. It's a mistake. So we look at a certain energy level, we look what is the infimum of this action dissipation. Again, this is 0 or greater than 0. So we look at this infimum for all potential, for all configurations, for all potential orbits which lie on this energy level. And then you take supremum over all energy levels. So it's really a variation definition which I will make a picture on the next slide, which will try to give you a more intuitive feeling what this is. But it seems that this is really a useful quantity, which is related to, as I said, to delta 1 and delta 2, delta 0 and delta 2. Now, properties of delta 1. Again, this is delta 1. I'll make a picture in a second, and then I'll explain why this is useful. So the first property is if delta 2, let delta 2 be the angle of splitting for a minimax homoclinic. So I'm not entirely precise here. So the assumptions are, to clarify this lemma 2-1, M rho is an O'Brien matter set with rotation number rho. So the assumption is that M rho is uniformly hyperbolic. So it has well-defined stable and unstable manifold. It has also in other cases, but in this case, the standard uniform hyperbolic theory applies. So this is, for example, true in this case, because this is just hyperbolic fixed point, which is the entire O'Brien matter set, just one fixed point. It has a stable and unstable manifold. And then assume that there is a so-called minimax homoclinic from the O'Brien matter theory. Again, this is exactly the case here. And that delta 2 is the tangents of the angle, or the angle for small alpha, the case this is the same. Then this quantity delta 1 is strictly greater or equal than delta 2, where this is some absolute constant. So my point is, if you know the angle of splitting, then delta 1 is proportional. Shoot.
What is an angle here? Because angle is not invariant after the map.
Yes.
So what is the angle?
The angle can be defined in different ways. Huh?
Just one, please.
Okay, just one. So this brings me to the proof. Okay, so the proof actually uses the following, and I'll then explain what the definition of the angle is. So this is the Aubry-Bazanson-McKay result, which shows equivalence of a phonon gap for Frankel-Contorra models and uniform hyperbolicity. And this result says that if we have a closed family of configurations which correspond to orbits, and if this is uniformly hyperbolic, then the second derivative of h, where h is formally written as some. This is a formal sum, but this is a well-defined operator on L2, and so that this is invertible. Sorry. So it's an invertible operator. And when I say angle, I'm actually referring to this lower bound of this operator, which can be related to, in a certain way, to the angle. Not happy? Okay. So, and this is actually the proof, because the proof how to relate delta 1 and delta 2 then goes approximately like this. I'll just make a one-dimensional picture, which is a little bit wrong, but it will give a little bit of an idea. So this is, let's say this is a gap in a Cantor set, and this is the value of the action. So what is delta 0? Delta 0 is the gap between 0 and the minimax value. So what is delta 2? Delta 2 is actually the second derivative at this point. Everything is, of course, in a Banach space, but I'm trying just to make a simplified picture. Second derivative. And what is delta 1? This is certain energy level, any one between 0 and delta 1, on which one can bound from below the slope. And in a way, why, if you know delta 2, if it's really an invertible operator, then locally this energy or action behaves locally like this value plus a linear operator which is invertible, and then one can really find an energy level on which one can bound from below the derivative of E, which is indeed just the function D. Now, the second lemma is that the following is equivalent. Again, I'm using the wording no km circle with rotation number. Delta 0 is greater than 0, so this is equivalent. 2 is just the standard statement from the Aubry-Mother theory. This is why this delta 1 is interesting, because whenever there is no km circle with this rotation number, then this is greater than 0. This is perhaps the only not entirely trivial result today. What is the proof of this lemma 2-2? So it basically means, just to step back, that you don't need hyperbolicity to be able to say that this delta 1, which I claim measures transport and instability, you don't need hyperbolicity for this delta 1 to be well defined. So why is this so? So let's look at the definition of D. If I'm very sloppy, then I will say that delta rho of y is equal to the norm of derivative of rho at y. This is not exactly true because I have chosen a particular Banach space, but if I was working just in L2, then this would be really the norm in L2 z square. And what does Morse-Sard theorem says? Morse-Sard theorem says that the set of energy, or for any function, if it's smooth enough, that for the measure of sets of values for which there is some point such that the derivative is equal to 0, has Lebesgue measure 0. And Morse-Sard-Pohojaev lemma, it's a theorem actually published, I believe, in 68 or 69, is a type of Morse-Sard theorem for infinite dimensional spaces. It works for Fredholm operators and with a certain conditions of smoothness. And it actually does work in this case. So one can really find energy action levels for this. Whenever this action is not identically 0, at least this dissipation is bounded from below, and then one uses compactness. It's actually not 0, and then one uses compactness to find a bound which is strictly bigger than 0. So again, I will not go into details of the proof. For the time being, just trust me. The point is this delta 1 is really strictly greater than 0 whenever there is a gap in a Cantor set, or whenever we don't have the entire circle as the Aubry mother set. Then the property 3, which is useful, this follows pretty much from definitions, is this delta 1 is actually lower semi-continuous, which means if we take any closed set, any compact set of rho, we will be able to bound this delta 1 from below by a number which is greater than 0. And then a conjecture that this delta 1 is actually possibly always, or at least generically proportionally to delta 0. And this is actually the explanation why. Because delta 0 measures oscillation of the action, and delta 1 claims that there is a certain level of the action on which derivative of this action is bounded from below, or the norm of the differential. So this is a conjecture which would basically relate delta 1 to delta 0 to delta 1, and then as I will express certain properties of entropy in terms of delta 1, this would also relate it explicitly to delta 0. Okay, now why this delta 1 is useful? What I'm trying to do is I'm trying now to prove just a standard shadowing theorem or shadowing lemma, but without any hyperbolicity assumptions. So again, so here are the assumptions. Rho k is a sequence of rotation numbers in a region of instability. So there is no invariant circle, homotopically non-trivial as an Aubry mother set in this segment. It's a segment. Then tk is a sequence of times. These are integers. L is a large enough integer. I will define L later. And then we choose a sequence of heteroclinic real orbits which join, connect this delta rho and delta rho k and delta rho k plus 1 with jump and take k. If these two numbers are close enough, then it's a standard fact. It's not difficult to prove it variationally that such an heteroclinic orbit exists. What I want to show how one can connect an infinite chain of them. Whoops. Delta 1 is the minimum of this values delta 1 rho across this segment, and by lemma 1.3, which is that this is lower semi-continuous, we know that this lower bound is also greater than 0. So this is a lower bound which is again strictly greater than 0. And then xj is an approximate orbit which you get by gluing all these heteroclinics by taking pieces of each around this jumping point tk, L to the left and L to the right. And the question is there a real shadowing orbit close to X? I will not define precisely what this close means, but it means exactly what we want. We want that this is close, and that it also is very close to Aubry mother sets along the way. And so this is a non-hyperbolic shadowing theorem. or lemma. I'm a little bit cheating because I introduced another constant which I will specify a bit later, but for the time being, let's just look at the relationship between delta 1 and this statement. This statement says that as long as L is large enough, proportional to 1 over logarithm of this delta 1, then there exists a real orbit close to x. Again, there was no hyperbolicity assumed. So the only thing one needs to know this delta 1, which I said is non-zero whenever, or greater than 0 whenever there is no Km circle. This theorem is actually not new. Mother has shown that like quarters of a century ago. The only thing which is new is this bit. So his version is not quantitative. He has shown that one can find lots of shadowing orbits, also of infinite length in the region of instability. But what I really wanted to do, I wanted to see and variation show how quickly one can move around. And again, this delta 1, if you know angle of splitting, then you know this delta 1. So this is what I'm saying. You are able by this method to incorporate geometric information if you have it. Also, for example, what I didn't say, let's say that this homoclinic orbit does not correspond to transversal intersection. That it is actually homoclinic tangency, but that you know how this action behaves around this point. So let's say that the action doesn't behave as in the transversal case as I would say delta 2 x squared. Let's say that it behaves as some constant times x4. If it's like a cubic or whatever homoclinic tangency, you can still, by using this information, you can actually estimate delta 1. So what I'm saying, you can quantify in a number of cases this delta 1, if I believe so. I haven't checked in one single case, but just philosophically one should be able to do it. Okay, why is this neat? Because then one can express topological entropy and speed of drift in terms of this delta 1. So again, it's known by Mother and many others in a qualitative way. If there is no invariant, if over Mother set is not invariant circle, then you can find some chaos. You can find a set of positive entropy, but this is actually what the topological entropy is. And this is actually how quickly you can move around your phase space going from one side of the region of instability to the other. Okay. Very briefly, outline of the proof. The proof uses formally gradient dynamics of the variational principle or dynamics of so-called Frenkel-Kontarova model on the entire Z. So what is new here? What is the idea that I actually already had this in my talk a year and a half ago? So the idea is the following. When you variationally construct orbits, you basically typically look at minimizing action over finite length. So instead, what I really want to do, I want to do at orbits of infinite length, and I want to do at invariant measures. And I really look at properties of this equation. This is an equivalent of something like this. And it's semi-linear parabolic differential equation or reaction diffusion equation. So, and how one proves that there exists such an orbit by actually stealing ideas from PDEs and constructing an invariant set. Constructing an invariant set with respect to these dynamics. Why is this delta 1 important? Because this delta 1, actually, you have this kind of action dissipation law, and this delta 1 gives a lower bound on dissipation. So what is this? This is a standard formula that one sees in study of dissipative PDEs. Change of energy, in this case of action, on some large domain is equal to minus dissipation plus some flux to the boundary. And how one constructs an invariant set. But then on a certain energy level, one has lower bound on this dissipation. So this must be greater than some delta. And this F, if one chooses L big enough, is exponentially small. So what is the moral? That this energy level can never be crossed by these dynamics. And you have an invariant set. This idea actually seduced me to actually try to develop a bit these tools, because I believe it's a much simpler way and in a very physically natural way to construct orbits variationally. It doesn't require much work, as in, for example, Mother's papers and so on. You don't really need to precisely describe where your actual orbit is. You give a very rough description where it's going to be, and then you just know there is going to be one. It's in a way related to Sergei's talk and how you construct invariant manifolds, inertial manifolds. You don't really know where it is, but you just prove that it must exist by quantitative and qualitative arguments. This is in a way similar. Okay, now I won't bother you with too many technicalities. I just want to introduce one idea. So what is my goal now? My goal now is to use all of this to actually show how one can construct lots of interesting dynamics in a twist map. Going beyond just actual shadowing, how can one construct lots of interesting invariant measures and hopefully at least describe at least a part of the region of instability for an arbitrary area-preserving twist map? Okay, so I will propose a concept of a shadowing invariant measure. So a shadowing orbit is a classical notion, but I will propose a new notion of a shadowing invariant measure, which I think is useful because by using these tools from the first part of the talk, and this notion, one can actually embed lots of interesting invariant measures with prescribed topological and measure theoretical behavior in a billiard or in a twist map. So here is a definition. Let's take, it's an abstract definition. Let's take any compact metric space and S a homomorphism on this compact metric space. Think twist map in this case. And we take two invariant measures. This should be capital omega, I'm sorry. So these two invariant measures on this space. And let's say G is a sigma subalgebra of F. So F are all Borel sets, Borel measurable sets, and G is any sigma subalgebra. I will give a couple of examples. And we say that invariant measure mu, G shadows measure G shadows measure mu if the second one is a factor of the first one, and if for each set in this subalgebra G, we have that these two measures are identical. So in a way, there are two things that you require. They're both measures, invariant measures from the same set. You require two things. The first one is that the second one is a factor of the first one, and the second one is that they coincide on this G. Okay, two examples. So what does this general idea encode? What it enables? Example one. Let's say that the measure mu it's on some subset omega, and let's say it's supported on some set D0. This is a support. Okay. Then one can define a sigma algebra just like this. And if one inserts this into this definition, then measure mu, which is going to shadow this one, is going to be a measure which is going to have a support also in this D0, and mu is going to be a factor of this one. So in a way, in this particular case, you're going to control support. Let's say you want to find a measure which is a factor of, this is example 2. One can, by the way, define notions of conditional support. I'm not going to define that right now. The second example, let's say that you have a measure mu, and you choose any finite set, let's say 5 points, and you want to, which are in the support of mu, and you want to make sure that actually when you construct this new measure nu, that it's going to come, that all these 5 points are going to be in its support. Then you just take G to be generated by a basis of neighborhoods of each of these points. And again, in this way, this definition enables you to construct measures which, since you know its factor, you control its measure theoretical properties, and since you define a couple of sets on which you want these measures to coincide, you control its topological properties. So in a way, it's an abstract way to look for certain invariant measures which lie in a certain set. Why I need this? Because I will construct positive entropy measures, ergodic ones, which lie in a precisely defined part of the phase space. And I'm going to use this notion. This shadowing invariant measure has some useful properties. Again, I haven't defined the notion of conditional support, so I will just skip this one. But this one is useful. If mu is ergodic, then one can find, and if you know that this other measure G shadows mu, then you can, without laws of generality, assume that this is also a ergodic one. So these are just standard ergodic theoretical arguments. And the second one is a shadowing measure is going to have a metric entropy which is not less than the metric entropy of the measure which it shadows. Why I'm saying that? Because there is a way to construct shadowing invariant measures in a twist map. There are 4 assumptions which need to be checked. The first 3, so basically you define a mu. Let's step back. What is the idea? So the idea is the following. I have a big space, which I call X tilde, which is a subset of Rz. So these are not really only orbits of my standard map. These are all configurations. And I have a shift on this space, which is well-defined shift, which corresponds to actually the action of the corresponding area preserving map. But this S is defined in the entire X. And what is the idea? To construct, it's very easy to construct S invariant measures on this big space with certain properties, topological and ergodical, and then by using the variation approach that I mentioned a little bit earlier, you construct the actual invariant measure of the twist map, which G shadows this approximate measure. So in a way, this is an abstract tool to construct invariant measures in a twist map so that you control its properties. And how do you do that? Again, you use this formally gradient flow, but then rather than looking at evolution of individual configurations, you look at the evolution of this big invariant measure mu, and you find nu which is in an omega limit set with respect to weak star topology of mu, with respect to this induced semiflow in the space of measures. So basically, really, you use in an essential way all the machinery that I have developed. Now, what one can do with this? What is neat is actually this entire machinery works for Tonelli Lagrangian sonotores in any degrees of freedom. So one can define an analog of this dynamics. One can prove that this equation has solutions, and then one can construct invariant measures for actually arbitrary Lagrangian system on a torus in arbitrary dimensions as soon as one can construct invariant sets of this dynamics, which is critical. This is this condition 4. So basically, construction of invariant measures of a twist map reduces to construction of invariant set with respect to the dynamics I have explained. Now, lots of talk. Let's show an example of a result. Again, I'm sure that John Mather would say I can prove that as well by my tools, but this proof, once you have the machinery, this goes really easily. So let's say the following. Let's take one region of instability of an area preserving twist map. M row are Aubry-Mather sets for each row. So in each case now, as this is a region of instability, by definition, this is never a circle. This is either a Cantor set or a collection of periodic points. And let's choose any closed subset of this interval. And result is that there exists an ergodic positive entropy invariant measure mu, such that exactly those whom we have chosen are in the support, and all the others are not in the support. So this is just an example of what one can do with this machinery. So you just take any family of Aubry-Mather sets, you can construct a horseshoe, so an ergodic positive. Ergodic, it's important because we are not cheating, we are not putting together different measures. It's one single measure, ergodic measure, positive entropy measure with a prescribed support. And an additional consequence of this approach is that actually you can estimate even its metric entropy in terms of this delta 1. So, it's still very much an open question how big this region of instability is, but what this result shows that if you have a twist map which is in a region of instability in a twist map, the number of positive entropy measures that you can construct is simply enormous. I don't know what the implications of this are, but again, this is just one example of a result. So one can use these tools to actually construct lots of things, to embed different types of statistical behavior in a given standard map. So what I'm trying to do, I'm actually trying to do a rigorous construction of what was done in this 84 paper. In this 84 paper, that was an ad hoc construction how this delta 0 quantity could be translated into some sort of Markov chain dynamics on a subset of orbits of a twist map. Precise, even though still pretty much almost certainly on a set of Lebesgue measure 0, but still one can do precisely this construction by transition probabilities which are not proportional to delta 0 as in this paper, but to logarithm, 1 over logarithm of this delta 1. And I'm not going to bother you more. I'm just going to mention that what I've succeeded to do is actually to use these techniques also in this case, which is basically 2.5 degrees of freedom, slightly generalized famous Arnold's example, and that one can also construct as long as there are no topological barriers to diffusion. There is no hyperbolicity needed in terms of intersections of stable and unstable manifold. One can construct lots of positive entropy measures, similarly as in the twist case. So I'm going to skip this and just show a couple of papers. This work has been posted in the case 2.5 degrees of freedom with all the tools that I mentioned worked out in June in arXiv. The twist map case I haven't written down yet. I don't know how interesting it is in terms of new results, but again, the tools are useful. I would be very much interested if any of you has any specific examples. Some of you mentioned higher degree Melnikov theory, which may be required to resolve a certain step in a problem. Also, the homoclinic tangencies appeared in your talk. So I'm interested to hear if there are some specific examples where these tools that I mentioned could be used to give some specific original insight. Thank you.
Thank you very much. We have time for questions. Okay. Would you show please your theorem 5.1? I've got a naive question to that theorem.
Okay. Yeah.
Okay, so when I look on this theory, I have a following picture in mind, which may be correct or maybe not correct. So you tell me. So suppose you take this band where you are looking between two rotational numbers, and then you find there just one horseshoe. So just periodic orbit, intersection, transversal, so we know that there is a horseshoe there. And then we assign to that horseshoe an invariant measure, say 1/2 in total. So we assign to this horseshoe an invariant measure which is 1/2. And then we take all different measures which are obtained this measure 1/2, giving 1/2 to any other invariant sets which may appear inside this strip. All these measures will have a positive entropy because of that horseshoe, and doesn't tell us anything about the dynamics, because with a Lebesgue measure, we know that the measure of a horseshoe is 0. So what is the difference between my suggestion of constructing a measure mu in yours?
Because this is an ergodic measure, and you actually summed two measures so that the new one will not be ergodic. You take one. Huh? Sorry? You take 1/2 of a... You can't hear me? Now you can. So you gave me an example of a measure which is not ergodic. You take 1/2 of your invariant measure close to a periodic set and 1/2 of something else. This is not an ergodic one. Okay, this is a convex combination of two ergodic measures. So this is exactly why this ergodic is important and why this lemma is not entirely useless.
Okay, minor modification. So we find an infinite number of horseshoes because we know that each of these Abri-Mazur set is a limit of periodic orbits. So there should be an infinite number of horseshoes.
Absolutely.
And then if you just put an invariant measure on a horseshoe, we get ergodic positive entropy invariant measure.
I don't follow you.
So I mean that I can construct, probably, if I can just detect an infinite number of horseshoe inside this instability zone, which is probably true because we know from a general theory that there are infinitely many hyperbolic periodic orbits.
Yeah.
So then we can find infinite number of horseshoes. We can take any of these horseshoes. Okay, then invariant.
No, these are really different horseshoes. So you cannot combine horseshoes that you construct by other. These are really different ergodic measures. And the way they're constructed, they're very much different. So each of them is a different embedded, in this case, Bernoulli subshift. So it's really different ones. They're ergodic, they have different entropy. It's not a convex combination even in terms of integrating a family of invariant measures. So it's ergodic, the composition of each of these measures is just a single measure, however you do it.
Any other question? Regarding your definition of the quantity delta 1, the definition that you give is suitable for analytical proofs, but it's a nightmare from a computational point of view. Is there an equivalent formulation or an equivalent definition of that quantity, better suited for numerical computations?
Okay, so I was thinking about it, and I'll tell you ideas that I have, which are really very, very raw ideas. So a couple of instances where you can estimate it is, first, if you know one homoclinics and any information if it doesn't need to be correspond to transversal intersection, but if it's like a quintic homoclinic, you can still, by a perturbation argument, estimate delta 1. The second is in anti-integrable limit. If you're very far from integrable, then you pretty much know the regions of your space where they are certainly not, you cannot find because the thing is simply too steep. You cannot find equilibria, then you can bound this delta from below. But the thing I'm really interested in is to try to, at least in the case of twist maps, relate delta 0 and delta 1, at least generically, and then this would really be the missing step in linking this all together. I think this could be done, but I haven't succeeded to do it.
Okay, thanks.
I think we can continue discussing in the poster session. So let us thank our speaker again. Thiago, any announcement?
So the posters will be below the library where we had our lunch. So before the posters, we will gather in these, what we call the secret gardens here of the Institute, and we take a group photo. That should take 2-3 minutes. So then for the conference dinner, that will be at 7. The restaurant's called Barone. So if you leave the Institute, or if you leave the campus by the south entrance, basically you walk all the way. So when you leave here, you turn left, walk all the way, you're going to hit the south exit. You turn left, you're going to see the restaurant's called Barone, yeah? So that's it then for today. Oh, the last one. Tomorrow morning, we're going to go to the farm. So we meet here in front of this building at 8 o'clock. The bus is going to leave 8:05. Then we go to this farm, it's called San Bento, yeah? Thank you very much.